Hello everyone, I'm Johanan from SSN College of Engineering, and I'm here to present our work titled Development of a Speech-Enabled Interactive Enquiry System in Tamil for Agriculture. This here is my outline of my presentation. First, I'll introduce the application to you and talk to you about who the beneficiaries are. Then we'll talk about the architecture of the enquiry system itself. Then we'll give some special attention to the recognition aspects of the application, which is actually of prime importance. We'll also look into the speech synthesis and database aspects as well. Finally, we'll discuss the performance aspects of the system. So an enquiry system is an application which provides some sort of information to the user on the provision of an input query. So a speech-enabled inquiry system is one which can do this through a much casual mode of communication, that is speech. In our system, we concentrated on some prime aspects of agriculture in Tamil Nadu, namely crop production and protection, concerning paddy, ragi and sugarcane. A motivation for having such a scope of work is that these are the most commonly cultivated crops in Tamil Nadu, and most of the queries would be concerning these crops. And once this is addressing the other crops would be much easier. There are some existing enquiry systems in India, but they focus on a small segment of agriculture, namely commodity prices. We tried to address a much broader segment of agriculture and also try to keep the application as user-friendly as possible. Okay, so who are the beneficiaries here? First and foremost, the farmers are the beneficiaries because it is mainly directed at them. Secondly, agriculture-focused call centers can use this. They can use this as a front end. Thirdly, it could be anyone who's interested in agriculture or looking into a future with agriculture as their livelihood. This here is actually the block diagram of the enquiry system itself. We will look into each of these segments in detail soon, but what I want to point out to you is in this block diagram is that we have mainly four components. The web interface is one, which is the front end. The speech recognition system, the speech synthesizer, and a database containing information about agriculture. We will look into each of these now. Before that, I want to focus on the basic flow of the enquiry system also. An important decision in making this enquiry system was when we had to decide the use case scenario, like how a person would be using the system. Would the user directly be asking one big question? In that case, we would have to look out for some keywords and then fetch relevant information based on those keywords. But this could also turn out to be quite tricky, as the user could form any simple question in any number of ways. So we thought of a simpler approach that confines the user to just the keywords. Instead of letting the user ask the question, we ask the user a series of questions, each one narrowing down the query. This is similar to navigating a tree, where each node is a question and the answer will guide the user to the next question. And when he reaches the leaf node, that would mean that our inquiry has reached its final form. At this point of time, we can give the user the answer to his query. Here we have an example flow. Some of the stages have been left out in the middle for the sake of clarity. So after Pair Sagubadi, we have left out some of the stages. So the light blue boxes are the questions that the system asks the user. The green boxes are the replies from the user, and finally the dark blue box at the end of the flow is the answer that the system gives the user. So at the moment, the application is a web application, but it could also be turned into a phone-based application in the future. The user communicates mainly through the mic, and the system talks back to the user through the speakers or the headphones. At the same time, we have the corresponding text being displayed on the screen as well. Okay, next we move on to the speech recognition system. The speech recognition system is the most important component of the enquiry system. It basically converts speech to text. In the current work, we use a speaker independent recognition system, which means that it would work on any new speaker as well. We perform isolated style recognition on keywords, which means that we would be recognizing individual words rather than a continuous string of words which make up a sentence, as in continuous style recognition. We also use triphone models instead of monophone models, since triphone models contain contextual information as well. This will help in improving the performance of the system drastically. Also, to improve the recognition performance, we opted for multiple recognizers in the same system, assigning one for each stage. We call a series of a question and its corresponding reply to be a stage, basically. Due to this, there is reduced confusion now, since the recognition system has smaller number of keywords to pick from as compared to a situation where we attempt to recognize a keyword from a full list of possible keywords. Next, we move on to garbage models. So, although we have carefully framed the questions so that the user will reply with just the keywords, there is still some possibility that there might be some additional keywords, additional words as well in the user's utterances. This can be handled by using something called garbage model. Usually, a keyword model would correspond to just one keyword and its variations as uttered by different speakers over different time. But a garbage model does not correspond to any particular keyword. Instead, it is trained on a group of words in an attempt to model out of vocabulary words. In our work, we grouped words with similar phoneme counts to create these garbage models. So, if the word recognized is wrong, based on some undesirable circumstances, and we proceed to the next stage also based on this wrongly recognized word, then the user would be directed along an incorrect path and finally end up with irrelevant information. So the application asks the user to confirm the response. For example, in the first stage of the example flow I showed you, the application would ask the user, நீங்கள் nel என்று கூறினீர்களா, for which the user can reply with arm or illai. If he says arm, for example, it would go to the next stage, or else it would ask the user to say the keyword again. But if you are going to confirm with the user in every stage of the application, then it could cause some considerable delay in getting the final answer from the system, and it would also be annoying to the user, right? So we opted for a likelihood based approach that confirms only when the system is not confident of its recognition. This is a two-phase process which has a training phase and a testing phase as well, as we'll see in the following slides. So in the training slides, we will attempt to recognize each example of each word in the training set with its corresponding recognition system. So this will yield two log likelihoods that correspond to the first and second best hypothesis. Usually, recognition system considers the first best hypothesis as the recognized keyword itself, but here we take the ratio of these two log likelihoods, which is sort of a measure of how confused the system is with respect to recognizing a particular utterance. We do this for all examples of all keywords. We then take the mean of the ratios that correspond to a particular keyword. This is set as the threshold for that particular keyword. So whenever an utterance is recognized, if the ratio exceeds the threshold, then it is assumed that there might be an error in the recognition. But there are 4 cases of interest here as shown in the table here. Cases 1 and 4 can be ignored as they are ideal scenarios. I will explain. For example, with case 1, when the recognition result, which is the first best hypothesis, is wrong, then if the ratio is also greater than the threshold, then we have an ideal scenario and we do need to ask the user for a confirmation. Similarly, for case 4, when the utterance is correctly recognized, there is no need for a confirmation. For case 3, also it also does not pose a serious issue. The question would be redundant, but still it is fine. But case 2 poses an issue and needs to be avoided at all costs. In this case, although the recognition is wrong, the confirmation will not be asked since the ratio is not greater than the threshold. so it causes a problem. So this should be avoided, and our threshold is mainly set on based on these consequences in mind. The speech synthesis system is next. So this is mainly responsible for converting the text to speech. There are two main speech synthesis techniques available at the moment. One is the unit selection synthesis technique, where we concatenate corresponding waveforms to make a sentence, but this requires a lot of disk space. The other approach is a statistical parametric approach, which we have used here also, the Hindenburg-Markov model based speech synthesis. Throughout the system, we opted for a speech synthesis system rather than recorded waveforms for two main reasons basically. One, they require less memory as compared to recording and saving them as audio files. And two, in case the answer for a particular question changes over time, or if we need to make some modifications to the questions we ask the user, we don't have to worry about re-recording the speech again, since the speech synthesizers does this on the fly for us. So next we'll move on to the database. So we have a textual database and a speech database. The textual database, the questions and the answers are stored as flat files basically. We also have a lot of map files and tables also stored as flat files that help us with the programming, the question answer logic and all that. Most of the data we have here are derived from the Agritech portal hosted by Tamil Nadu Agricultural University. We also need a speech database for building the recognition system. We collected 432 one-word responses from 16 male and 16 female speakers to train models for the recognition system. Most of the speech speakers provided multiple variations of the same words as well. So that was that. And next we have the performance finally. The performance we finally obtained considering all these techniques discussed above was 98.4%, which was pretty good. We also reduced the processing time considerably by employing the likelihood based approach that cut down the average time spent on each stage by around 27%. This is based on the probability of asking the user for a confirmation, which was measured empirically over time. And these are our references. I thank you all for listening to my presentation patiently. Thank you.